and I built a prototype with shape memory alloys, and I investigated use of shape memory alloys and how they could simplify prosthetics and make them cheaper without sacrificing functionality. Okay, so in this presentation I'm just briefly going to go over the design process, how shape memory alloys work, the previous iterations of prototype before I came to the one that I have now, the prototype that I have now, and the data I collected along the way, and finally the conclusions that I drew from the data. So the problem with today's prosthetics, there are obviously some really great prosthetic hands out there. So for example, the Bionic, the iLim. As you can see on this graph, they are really, really expensive and in the tens of thousands of dollars. So for example, in developing countries and for returning veterans, most people who need these prosthetic hands can't afford them. So there are some hands designed to be distributed in developing countries to be cheap, so $50 to $100, but they are pretty unsophisticated. So all of 4 fingers are actuated simultaneously, and in some cases the thumb isn't actuated at all, so you can't move the thumb. Go ahead. So as a solution, I propose to use simple aluminum to make it easier to build, and replace motors with shape memory alloys, and replace rigid joints with super elastic alloys, which we'll talk about now. Now, shape memory alloys are alloys of nickel and titanium, and they have this special stress strain curve, which measures how hard it is to bend a shape memory alloy wire or deform it. And they basically can be bent way more out of shape than a regular metal. So if you bend a regular metal, very soon, very small percent deformation, it begins to be irreversible and bends permanently. Whereas shape memory alloys, you can bend them way further out of shape and have them still return to their original shape. Next slide. And this is what they look like at the crystalline level. And the ability to have this property of shape memory stems from being able to undergo phase transformation while still solid. So they can exist in martensite and austenite phases the way water is solid and liquid. But both of these phases are solid, and they depend on how much stress the material is on and the temperature. Go ahead. And the way you measure the stress strain curve that I talked about is with an instron tensile tester. So here there's a wire clamped into the tester, and it pulls on the wire and measures how hard it is to pull on the wire. And this is a close-up of the graph that I made with this machine. And so as time progresses and the machine pulls, it measures how hard it is to pull, and then it releases it until it measures 0 load. So here is the extension, and here is the load. When it comes back to 0 load, you can notice it hasn't contracted all the way back to the origin. So then I ran an electric current through the wire to heat it up to make it change phase. And what this does is it makes it try to contract back to its original shape, and that is the shape memory. But instead of letting it contract back, I held it in that position and measured how much load it exerted onto the machine. And this is pretty significant, so that's this line over here. It exerted about 14 to 15 pounds onto the machine, whereas it only took 10 pounds to extend it to that distance in the first place. So that's very significant in terms of actuation, because if you have 2 of these wires that you stretch and they are on opposite sides of a lever, so let's say you have a lever and have a wire 1 and wire 2, you can heat up wire 1, have it contract and stretch out wire 2, but still have force left over to pull a string. Go ahead. And so to test this hypothesis that shape memory alloys can be used as actuators, I built a modular palm that I could attach various different shape memory alloy or different actuators, and then a finger that was very simple, used a super elastic wire, which is just a shape memory alloy wire, but it acts more like a spring. So at room temperature, it always tries to return to a pre-designed or parent shape. And in this case, the parent shape was a curled up finger. So when you pull on a string, it straightens, and when you let go of the string, it curls back up. Go ahead. So the testing criteria was it took about 2.5 centimeters or an inch to fully straighten the finger. So the actuator needed to be able to pull that far. It needed to do it pretty quickly, and it needed to be efficient, so about 5 volts, 2 amps or less, which is about what your cell phone uses. And also cost effective, obviously, so under about $50. So my first prototype, I made these wires. I heat treated these wires to remember a parent shape, which was in the shape of a corkscrew. So let's say you have a straight wire and it remembers a corkscrew shape. If you heat it up, it's supposed to contract into a shorter distance, and therefore you can have a actuator that pulls back and forth. However, it's really weak, so it didn't actually work. The next thing I tried was an M shape. That also didn't work. And the zigzag. This was the first thing that actually worked. So it was straight at first, and then when you heat it up, it contracted into a zigzag. And I was able to pull the string far enough to straighten the finger once, but then since all the force is being done by these corners here, it fatigued really quickly and stopped working. Then I tried a corkscrew with more wires, but that also didn't work. Finally, I came to the realization that I could just use the straight wire and pull on it and then heat it up and it contract. And the advantage of this was it had suddenly a lot more force than the previous iterations, but the problem was it could only contract a short distance. So it was able to move the finger, but not very far. And so to solve that problem, I added some pieces to add leverage. So I had a pulley that increased the leverage by 1 to 3, and then a lever that I could bury the leverage. So I have the shape memory alloy wires on the either ends of the lever here and here, and I have a string that pulls and straightens the finger. So go ahead. And one more time. Should play the yeah. So if you heat up this wire with an electric current, it actually contracts and pulls on the lever, which straightens the finger over here. And if I move the wire to the other wire and heat that one up, it helps it to speed up to contract back. Next. So as I mentioned before, this finger is default shape is curled, and then when you pull on a string, it straightens, and then when you let go of the string, it curls back up. And that's not a very good design for a finger because it doesn't have very much force when you're grabbing things. So in the next iteration, I focused on changing the finger design, and as you can see here, there's a super elastic alloy wire here. Again, it's just a really good spring, and then a tendon that pulls, and when you pull on this tendon, it contracts the finger. So its default shape this time is straight. When you pull on the string, it curls up. Can you go next one? And this is the video. So when I heat up one of the wires, it contracts, and when I heat up the other wire, it straightens back. And as you can see, there aren't any motors here. It's just the super elastic shape memory alloy wires doing the work. And the advantage of this is each of these wires is only a couple cents, whereas an electric motor used in some of those most sophisticated designs are about $30 each, and they have 10 to 15 of those, so it contributes to each part of that cost, and that is saved in this prototype. Go ahead. So some of my data, I measured how far it was able to contract in each iteration. Distance, and 2.5 was a satisfactory value. And so you can see the last two prototypes were able to fully contract the finger. Go ahead. And I also measured how long it took, and got pretty close to the goal with my last two iterations, about 1 second. And how I also measured how much electricity was needed, so about 3 to 5 volts in 2 minutes. And yeah, go ahead. And here's the superposition of the curled up finger and the straight finger, and I was able to demonstrate that shape memory alloy wires are a good substitute for motors as actuators. The other thing that is special about this prototype is the finger design. Regular fingers use rigid joints or ball bearings in some situations, and that has the benefit of being easy to control, but however, if you hit it too hard, it can break, and then it's very expensive to replace. And with the thumb, limits the design very significantly. So in a prosthetic hand needs to be able to move the thumb in a variety of different ways, and so some of the really sophisticated designs to accommodate you're like shaking a hand or gripping something, that you need to shift your thumb into a different mode, and that's a pretty awkward thing you have to do. But with this finger design, since it has a flexible core, you can just add another actuator and bend the thumb into any direction you want. Next. So, what about the cost? These are the sophisticated hands again on a logarithmic cost scale, and the prototype only cost about $50. Now, obviously, if you add more fingers, it's going to be more expensive, but if you also manufacture in bulk, then the cost goes down again. So it has the potential to be the same functionality as this, but it already is the same cost as the cheapest ones. So what's next? The actuation, which was on the forearm, is a little bit too big, and that can be made smaller by figuring out what's the best leverage, and then removing the levers and putting pulleys instead, which are smaller and easier. The shape memory alloy also gets pretty hot, and so you need to cover that so it doesn't hurt anybody, and hopefully get the patent. Okay. And I would like to thank my 7th grade biology teacher and Mr. Meshina. I know that sounds a little bit silly, but if it weren't for him, I would never have gotten excited about science and technology. I'd also like to thank Dr. Kumar, my chemistry teacher junior year, who helped me throughout this project and helped me get approval. And finally, I'd like to thank my parents, one more time, for teaching me how to use the milling machine and supporting me even though aluminum shavings started accumulating all over the house. Go ahead. And if you have any questions?
How is the like the force of this memory alloy compared to like a normal finger gripping or any of the prosthetics?
As of right now, it's probably a little bit lower. So the finger has, I don't know, a couple pounds, but that can be fiddled around with by adding. If you add more shape memory alloy wires, you can make it stronger and not use terribly too much more energy. Yeah.
Are the wires pretty durable, or do you have to replace them periodically?
As long as you stay within a certain amount of load and contraction distance, it can be cycled millions and millions of times. So if you, there are certain specifications you'd have to say, so don't lift too heavy loads and it'll last longer. But if it does fatigue, or if it does, it's probably not going to break, but it could fatigue. If it does fatigue, you can replace it pretty cheaply.